Okay, so we'll continue with section 1.3, and at this point we're looking at the idea that if so we know the limit as x goes to c of g of x this time is equal to the L. So this is at the top of page 61. Then if we know the limit as x goes to L of f of x, now I think this is kind of weird, but they say is f of L. I'm trying to think if that's, well, I guess that, yeah, that would be required. So, yeah, okay. So you don't want to just say k. It is important that it is, the function's defined there, of course, right? See, if I just put a k instead of f of L, if I just said, oh, and that's equal to k, well, I don't even know that f is defined there. But here I actually do need to have it defined there. So, so what we'll have then is, if we take the composition in this order, x goes to c of f of g of x, then what that is that the limit as x goes to L of f of L, but of course that's now a constant, so you just get f of L. Okay, so composition, as long as those limits exist and the function exists, so that's very important. See, is that the function needs to exist there, and you know, so that's kind of a subtle point though. But by writing f of L, it says it does exist there, and the limit as it goes there is f of L. Okay, so that's composition, and you know, they just you know, they're looking at something that we can do direct substitution on. You know, they've got an example, for instance, that says, oh, here's the limit as x goes to 0 of the square root of x squared plus 4. Well, for us, hey, that's a very nice function and so forth, and so I'm happy if you just say, oh, well, that's the square root of 4 equals 2. I'm good with that. Now, what they do instead of this is they say, well, this is a composition, and so they're looking at the fact that the limit of x as x goes to 0 of x squared plus 4, and they would go through the splitting everything up and so forth to get 4. And then they say, well, the limit as x goes to 4, okay, because that's that limit L, of the square root of x is equal to 2. Okay, so they're doing it that way. But again, for us, if you can just do a simple substitution, direct substitution, and everything's fine, you're not at an endpoint or anything like that, hey, great, just go ahead and do it. It's 2. Okay, then they also give this theorem 1.6. I'm not really going to go into that. It just says, hey, the trig functions are nice. Okay, trig functions can be directly substituted. Okay, they're nice, just like, you know, the square root of x plus 4 Substituted. Okay, there we go. So that's the theorem 1.6. Not a big deal there. You know, we can just use direct substitution on those functions. Okay. And you know, so pretty much then they go through and they use the technique I showed back here, or wait, on the previous video. Okay, they go through a few of these rational functions. Okay, so remember, a rational function is some f of x, or you could call it r of x. That's one polynomial, p of x, over another polynomial. So suppose, you know, I have something of a rational function. We did this in the previous video, and it turns out I get 0 over 0. Everything else is fine. So for instance, you know, if I have the limit as x goes to 2 of one polynomial, and we'll make these really simple to see, so, you know, x plus 3 over x minus 5, I can do direct substitution, right? I get 5 over negative 3. Great. And now, that's a little bit ugly to write it that way. Negative 5 over 3. It's a better way to write it. So direct substitution, fine, you know, not a problem. Another one, you know, I could have the limit as x goes to 1, and you know, if I have, you know, x plus 6 over x minus 1, that looks like, notice the arrow, 7 over 0. Okay, undefined, does not exist. Now, we would need to do a little more work to try to decide, do both sides head to infinity? Because anytime I have a constant over 0 like that, you know, this thing's going to head to either positive or negative infinity, but it matters a lot what sign we have here. So see, if x is bigger than 1, the top is positive, the bottom is positive, and as it gets close to that 0 with the, you know, because x is getting close to 1, we get a very big positive number. But if x is less than 1, you know, like 0.9 or 0.99, then this bottom here is negative, but the top is still positive, and so we would get a negative number that's heading toward negative infinity. So in this case, now, you know, it just plain does not exist. We wouldn't write something like equals infinity or negative infinity. So these are not a problem. Again, you need to, you know, you could look at the graph on something like this where you get a constant over 0 to see kind of what's happening. But generally, I can just plug things in, and I can see that, oh, well, at the very least, I know this one doesn't exist, and this one I can get by direct substitution. So the only problem is when you have these rational expressions where you get 0 over 0, because I'm not sure what to do with that, right? So here I have x goes to 2. Now I'm going to do this factored. You know, so if I had these polynomials such that when it factored, I had something like this, x minus 2 on the bottom as well, and you know, x plus 4. Well then, you know, so you would tend to get these unfactored, and so then the question would be, well, yeah, what is going on here? And you know, then you know, if you got 0 over 0 when you tried it in, then you would know that x minus 2 was a factor of both. Okay, if they're polynomials, has to be. That's the way these polynomials work, right? You know, so if 2 made it 0, one of the factors has to be x minus 2. So for top and bottom, and so suppose I factored it and I got that. Well then, that's where I use my properties of the limits, and this is the limit as x goes to 2 of x minus 2 over x minus 2, and times the limit x plus 1 over as x goes to 2, x plus 1 over x plus 4. And so now again, this part, that's 1, and then times, and here I can do direct substitution, so I get 3 over 6, and so this is 1/2. Okay, and so that's their thing called the dividing out technique, or the functions that agree at all but one point, that kind of thing. They're just these rational functions where the algebra ended up hiding some common factors, and so we look for what those are, we do our simplification, and then see what we get. But as in the first example, you know, had either the top been x minus 2 squared or the bottom been x minus 2 squared or cubed or something like that, but a bigger power, then we would have either ended up with 0 or does not exist, as we did up here, because we would have ended up with a constant divided by 0. So either 0 times a constant or a constant divided by 0. Okay, and that is what they're calling the dividing out technique. Now, they also mention rationalizing technique. Okay, so rationalizing. And so these are just some algebraic techniques to try to get at these things. And so their example is, for instance, this is example 8. And they're saying, oh, what's the limit as x goes to 0 of the square root of x plus 1 minus 1 over x? Well, notice the problem here is if I do direct substitution, notice the arrow again, not an equal sign. If I do direct substitution, all right, so I'll put a little ds up there for direct substitution, then what happens is, you see, I get this square root of 1 minus 1 over 0, which is 0 over 0. Ah, that's a problem. Now, but here I can't just factor or something because I've got that darn square root sign. But it's a book problem. They made something very easy for us. Now, just like before when we had, you know, the limit as x goes to 2 and we had x minus 2 over x minus 2 like that, and we said, oh yeah, that's just 1. Well, we can put that in. And so if we start here with the limit as x goes to 0, square root of x plus 1 minus 1 over x, but then we multiply by 1. But it's a very special 1. We're going to do the x plus 1. Now, I'm going to do a conjugate. I'm going to do plus 1, because when I multiply when I multiply these conjugates like this, I get the difference of squares, and that'll be a good thing. Square root of x plus 1 plus 1. But see, I just multiplied by 1, so I didn't change this at all up here. Right? So this is equal to that. And so then this, now I combine those limits all under one limit. Limit as x goes to 0 of the square root of x plus 1 minus 1 times the square root of x plus 1 plus 1 divided by x times the square root of x plus 1 plus 1. And you know, what a nifty little idea here is, because, see, now I get the limit as x goes to 0 multiply these, and again you get the difference of the squares. Well, the square of the square root of x plus 1 is just x plus 1. And then minus 1 squared, so minus 1. And then divided by, well, here we still have this x times the square root of x plus 1, like that. But now, you see, that's the limit as x goes to 0. And I could see that I could do this up at this step, but we'll write that all out. I get x over x square root of x plus 1, oops, parenthesis, plus 1. So you have this. Now, notice there's x over x. You factor that apart that way now. So now we use that multiplication thing again. And we limit as x goes to 0 of 1 over the square root of x plus 1. And, well, of course, that's 1. And now I can finally do my direct substitution. And so I get 1 times, and when I put in the 0 here, I get 1 over 1 plus 1, or 1/2. And so we finally do all of that, whoops, and we get 1/2. Okay, so this is this idea of rationalization, is that if I have a square root, either plus or minus another square root, or not. I mean, I can have it with just a square root. But if I have something that looks like a plus a square root of a plus a square root of b, or square root of a minus a square root of b, or square root of a plus b, or square root of a minus b, anything that looks like that, I'll just multiply by its conjugate. So here, if I have the top one, I'll multiply by that, and down here, if I have the top one, I'll multiply by this next one, and if I have the bottom one, I'll multiply by the top one. And the nice part is when you multiply these two things together, you get a minus b squared. Multiply those two things together, and you get a minus b. And so, that's just a nice little technique if you happen to come across something that looks like that in either the numerator or the denominator, and your direct substitution gave you something that said, oh, I need to work with this because I don't know what 0 over 0 is. Okay, so we'll call that good for this video.